Okay, thanks for coming. So what I'm going to do is I'm going to make a few very general remarks in line with this very general title, and then I'll talk about a particular sample problem that I've been thinking about recently. Okay, so I want to work in a relatively restrictive setting, so let me just consider the following geometric setting. Is this visible to everyone? So I'm going to look at X, a smooth complex affine variety. I'll just pick some embedding in some big Cn, and P, a holomorphic function. So a map from X to C, which is holomorphic. And maybe I want to assume for this talk isolated singularities. OK, and my title. Sorry? Oh, I mean, let's say it's a polynomial. I mean, the examples I'll consider are polynomials, but then I want to consider them in some more general category where they may not even be out. Sorry? It's not the exponential of a polynomial. Okay, so what's the setting I want to consider these in? So I sort of, let's say I'm thinking about a variety and an algebraic function on it, but I want to think of them in some sort of symplectic category. Okay, so I want to think of them in the symplectic category. That means, what do I want to remember from this data? I'd like to remember only from X its symplectic structure. Okay, so I want to think about X as the 2n dimensional real manifold coming from, with a symplectic form coming from restriction from this embedding into Cn. This is independent of embedding. And I want to think of P as a smooth map to C, which is a symplectic fibration with singularities. Okay, all I mean is away from some singularities, it's a symplectic fibration. Okay. Sorry? Oh, so I just take the standard symplectic structure on Cn. Yeah, for instance, that's right. Absolutely. OK, and so I'll think about this function P as a symplectic fibration with singularities, and I'm going to be a little bit vague about that. All I mean is away from some points. It's a symplectic fibration, and maybe I should say this talk's really about symplectic topology. But if you're interested in mirror symmetry, such pairs XP are often called Landau-Ginzburg models in mirror symmetry. And my interest in this sort of geometry arose in that setting.
Sorry.
Yes.
Question: is that related to Ginzburg-Landau? The Ginzburg-Landau equation?
Someone other than me, maybe. I'm not sure.
Yes.
Yes. OK. OK. So another question? OK. So there's a very large program in symplectic geometry, maybe initiated by Arnold and work, and ideas of Donaldson, Seidel, and many, many others, to understand this sort of geometry in the symplectic category. Okay, so specifically, you want to understand the relationship between critical points of this function P and symplectic topology of X. That might be one thing you might want to do, but you might want to also understand the relationship between the symplectic topology of P and what I might call the classical study of pairs XP in the algebra geometric setting. Okay, so Picard-Lefschetz theory, singularity theory, in the holomorphic setting, things like that. Okay. Really what I mean here is that, what should I say? If I restrict it to a general fiber, that's a symplectic submanifold. Okay, or if you want this structure group is symplectic for local transition functions. OK, so I'll say what a symplectomorphism is in a minute. But yes, yes. Yes, yes, such a singularity theory.
It's complex geometry, but your talk is symplectic geometry.
Yeah, so there's an interesting question that actually some of these invariants from complex geometry turns out they can be recovered completely symplectically. Okay, so that's one interesting punchline that I probably won't say too much about today, but I'd be happy to talk about it. Okay, so it turns out that some of these complex geometric invariants of singularities, like multiplicity, for instance, they're just an invariant of symplectic geometry. Okay, so this is very, very general statements. Let me say a couple more specific things in a minute. First, maybe I'll say a few basics about the geometry of the setup that might convince you that this is a reasonable thing from the point of view of symplectic geometry. So why might there be some interesting symplectic geometry lurking around? Well, let me draw a picture. OK, so here's our space X. Here's the function P. The map to C, well, it has some finite collection of critical values. OK, and what I want to do is I want to take some fiber that's not a critical value without loss of generality. Let's say it's 1. OK, and let me call M the preimage of 1. So I want to point out that in the symplectic category, I can associate to this pair xp this fiber with a distinguished map mu. So mu is some map M to M, which is an invariant of the setting. So how do we get this pair? What's the point here? So whenever I have a symplectic fibration, actually I have parallel transport maps. Okay, I'm getting rid of some technicalities, but I have symplectic parallel transport away from these critical values. Okay. So let me just say symplectic parallel transport. Yes, so all fibers are symplectomorphic, and this is the monodromy symplectomorphism. Okay, absolutely. You have to worry. Okay, so I think I'm sort of getting rid of some issues with, essentially, if you have a connection always, but you want to know that parallel transport exists and things could escape to infinity. And there's some study about how to deal with that. So
which monodromy element is it?
For instance, well, I was going to say it in a second, but let's just take this counterclockwise loop. Around everything. That's right. So at first pass, I'm just going to associate this coarse thing, which is the monodromy around everything. But of course, I can factorize it in different ways by monodromy around these critical values, and that's an interesting part of the study that I won't say too much about. Okay. Exactly. So the sort of fact that a symplectic fibration gives you this symplectic orthogonal, and that's the connection. Exactly. So because of this this idea that we have this canonical connection, if you sort of are careful and think about when parallel transport exists, when it does exist, all fibers are symplectomorphic. All general fibers are symplectomorphic. Okay, so a symplectomorphism, just remember, is some diffeomorphism that preserves these symplectic area forms. Okay, so all general fibers are symplectomorphic, and this is a monodromy. So this is the monodromy coming from going once around the base, and it's a symplectomorphism. Okay, so the first thing to say is we automatically get the structure from a setup like that. Now let me say a few more general words, and then I'll talk about the question I've been thinking about. So let's say we want to understand what's going on near a critical point. Well, let me do that in just one case. Let me talk about the case that the critical point is Morse, or the sort of Morse situation. So in the case that the critical point is sort of non-degenerate, this is the case that the local model for P is some sum of zi squared. Okay. By the way, if all critical points are like this is called in the symplectic category also Lefschetz fibration. Okay, so let's look near a critical point in the Morse case. All right, so here's my special fiber. which is the critical value. So here's the point, and here's the sort of special fiber here. Locally near the critical value, there's some model like this, a singular conic. And as I go to a general fiber, there's some model like this. And it turns out that, well, there's this classical notion of vanishing cycle, right? So you can see already there's some homology class, at least, that contracts to 0. And it turns out that actually this is a symplectic notion. This is, in fact, a Lagrangian submanifold. OK, so if I draw, I need to pick some data. I should draw some path in the base to my general point. And I should look at the set of points in this general fiber that parallel transport to the critical point. And this gives me a vanishing cycle, which is in fact a Lagrangian sphere. Okay, so it's some symplectic rigidification of this classical notion of vanishing cycle. So okay, so it's a Lagrangian Sn-1, and if I look at the entire family of collapsing Lagrangians, I get something which I'll call delta sub gamma. This is what's called a Lefschetz thimble. So this vanishing cycle lives in the general fiber. This Lefschetz thimble lives in the total space, and it's if you want a Lagrangian disk, or it's common to complete it, so we think of it as a Lagrangian Rn. Okay. Okay, so maybe one other thing to say about this basic setup. If I think about the monodromy around this critical value, as I mentioned, it's a symplectomorphism, and it's something called a symplectic Dane twist. Okay, so I think the first literature I can find on it was by Arnold, and it's been studied a lot by Seidel. So it's some symplectomorphism that's essentially determined by this Lagrangian sphere. Okay. Okay, so this is some basic reason why symplectic geometry automatically starts appearing in this story. And how much time do I have, actually? 6 minutes. OK. So you can use this setup. So here's something I'm not going to talk about. But I think it's very interesting, and a number of people have worked on it. You can use this setup to study germs of singularities, okay, of hypersurface singularities. Okay, what do I mean by this? If I take x just to be Cn, and I look at f, some function with an isolated critical point at 0, by basically the same considerations, there's a purely symplectic notion of Milnor fiber of the singularity. All right, that's sort of the general. It's the general fiber of f, but like cut with a small ball around the origin. And there's a monodromy, and this is very interesting, I think. But OK, so let's talk about the question that I've been thinking about. That's just sort of one instance of this general story. So you have to be careful, I think, about this. You have to make some modifications of this. But I mean, you can get something that's well defined up to symplectomorphism.
So you can get the symplectomorphism of a variety with boundary?
Yes. Yes, exactly.
Here you consider the most case.
Yes.
The d square, sum of d square, but here you consider germ of a general form of function, right?
Yes.
So you're interested in the more complicated.
Yes, you might be interested in the more complicated things. So how do you get at this thing? You might morphify this inside, near the origin, and you'll get a bunch of spheres. Okay, coming from all of those. New critical points, non-degenerate critical points that this function explodes into. Okay, so here's a sample global question about these sorts of the symplectic topology of such functions. And actually, the first reference that I found on it was this sort of book of problems by Arnold, some problem from the 70s in the Arnold seminar. but I actually learned about it first. It was posed by Seidel in the symplectic setting. So here's the question. Given this variety and this holomorphic function, what's the minimum number of critical values? Okay, so now I want to think about not critical points, but critical values of the function. Up to, so minimum number of critical values of p, well, this is not a sensible question unless I allow myself to deform p. So up to deformation. Okay, so up to deformation. And now you might ask, what type of deformation do you allow? Okay, and so the first type, let's say up to deformation through Morse singularities. Okay, so so what's the minimum number of critical values if you only allow non-degenerate singularities? Yes. So let's say in the holomorphic category, but you can talk about this in the symplectic category. And so any minimum number in the symplectic category implies one for the holomorphic category. So I'm going to study it in the symplectic category, but let me pose the question holomorphically. Okay, so case A, you only allow non-degenerate singularities through any deformation. In case B, you might allow through degenerate, but say still isolated singularities. Okay, so let me, so basically what I want to tell you, the punchline, the thing I'm working on right now is a way to use symplectic topology methods, particularly coming from Floer homology. Yes? Yes. No, not necessarily.
So in the case B, what's going to prevent you from just deforming the function to 0?
It's not isolated. The critical values aren't isolated. The critical points aren't isolated, right? Right. So the critical points are the entire manifold now, right? So I'm going to try to convince you that there's some obstruction here. In 2 minutes or however much time I have left. Okay. So there's a symplectic tool suggested by Seidel, which goes as follows. So let me think about this pair xp in the symplectic setting. I'm going to associate it to it a certain category, which I won't tell you about. I want to think about it as a black box. It's some sort of Fukaya-Seidel type category associated to this pair. So it knows about the symplectic geometry of singularities of p. It's trivial if p has no critical points. And now when I have a category like this, by a purely algebraic process, I can extract from it a ring, the Hochschild cohomology ring. Okay, it doesn't really matter what it is. It's a unidal ring. It's a unidal graded ring, if you want. It's a cohomological type thing. And from this ring, I'm going to extract a number. Okay, and this number is the cup length. Okay, so this is a standard invariant of graded rings. Okay, which is, I won't even write it down, but I'll just say it's the sort of the maximal length of nilpotent elements that cup together. So I obviously want to, I have a 1 here, so I can cup 1 with itself many, many times. So I want to get rid of that. It's just the maximum number of nilpotent elements that I can multiply together. Okay, so I'm going to state a theorem, and then I'm done. So I learned about this theorem from Seidel in the non-degenerate case, and I'm working on the case where you allow degenerate deformations. So that means that your original P is Morse, and you only allow deformations through Morse type P's. So this is, this is basically, so this is question A here.
Do you start with something?
Yes, I mean, so, no, what I mean is you start with anything, and you allow deformations to something Morse. Okay, in Morsification. Okay. And work in progress is going to handle case B, and it says that the minimum number is always greater than this invariant plus 1. Okay? So this is some invariant of symplectic topology, and maybe I'll just say in words that in some very simple examples, this thing can be arbitrarily large, even though smoothly you can collapse everything to one critical value. Okay. So I'll stop there. Thank you.